So in the second day of 8.2, we're going to be looking at something, again, called complex fractions, which we saw in the last section. These complex fractions are just a little bit different, though. If you look closely at this one compared to the complex fractions that we saw in the first day of notes, see how this one, like the 1 and the y minus x, are sort of separate? In the last section, in 8.1, we saw complex fractions where the numerator just had one rational expression and the denominator just had one rational expression. That made those ones a little bit different. These ones, in the numerator, we have two separate expressions. In the denominator, we have two separate expressions. So we're going to deal today with complex fractions like that, where you've got multiple rational expressions in the numerator and in the denominator, not just one. So there's two methods, like I said. The first method that we're going to be using, this first one way is to simplify the numerator and denominator separately. All right, so basically, just kind of deal with this as one entity, figure out how to get a common denominator here, then deal with this as one entity and figure out how to get a common denominator there. All right, and then you'll see how it becomes just like what we had the other day. So if we look at the numerator, in the numerator we have 1, which doesn't have a denominator, and then we have an x right here. So this LCD is just x. And then in the denominator here, we have a y, we have an x. Remember, we have to include both of those in our LCD, so our LCD would be an xy. All right, so like I said, we're going to treat the numerator and denominator totally separately. So in the numerator, we're going to make sure these both have a denominator of x. So the 1 clearly does not have a denominator of x, so we're going to multiply it by x over x. All right, so I'm going to multiply this times x over x. And really this one, it's like a 1 over 1, so you can think of that as a fraction as well. And then minus y over x, so this already has the right denominator. And then in the overall denominator, we have a 1 over y. And so if we look at the LCD of xy, it's missing an x. So we're going to multiply this by x over x, which is just a fancy 1. We're just trying to get it to be an equivalent expression that has the denominator that we want. And then plus 1 over x. So this has the x, but not the y. And so we're going to multiply this one by y over y, just a different fancy 1. Okay, so let's write down the next step where we kind of start to simplify everything up. So this 1 times x over x is just going to be x over x, and then minus y over x. Over, and then down here, 1 times x is x over my new LCD of xy, and then plus 1 times y is y, and then times, again, my LCD of xy. So now if you look up in this numerator, they both have the same denominator, so we can combine them up. So we can subtract the x minus y over the common denominator of x. And then in the denominator, they both have the same LCD here, so we can add the x plus y over the common denominator of xy. All right, so now this is the format difference that I was talking about. This format, there's just one rational expression in the numerator and one rational expression in the denominator, which is different from what we have over here. Here we have two rational expressions and two more rational expressions. So once we're in this form, we can do exactly what we did in 8.1, which is to just write it as a division problem. So we can take x minus y over x and write that we're dividing it by x plus y over xy, because that's basically what this fraction means. It means we're taking this piece and dividing it by this piece. So we write it like this. Next step, we know that when we're dividing rational expressions, we're really multiplying by their reciprocal. So my first piece stays exactly the same, but then I'm changing the division to multiplication, and I'm flipping this to its reciprocal. And then I just look for common things, anything that I can cancel out. And so the x minus y and x plus y are not quite opposites, so unfortunately we can't cancel them. I do have a copy of x here and a copy of x here that will cancel out. And that's actually it. So I have an x minus y times y. So I'm going to multiply that out. So I'll have an xy and then minus y squared over my denominator of x plus y. So let me remind you, and I will continue to remind you guys of this, just because you see common things doesn't mean you can cancel them. For instance, you cannot cancel those x's, and you cannot cancel these y's, and you cannot cancel these y's. This numerator is now one factor, and this denominator is now one factor. If the factors aren't identical, the way the x's are, you can't cancel them. The addition and subtraction makes that impossible. All right, so that would be your final answer. So on the next page, we're going to look at one more example where we use this method, and then we're going to learn a secondary method. All right, so in this one we are still simplifying each half separately. So if we look at the numerator, the c over d and the d over c, this one has a denominator of d, this one has a denominator of c, so our LCD needs both the d and the c. And then here in the overall denominator, I just have a denominator of c, and so that's my LCD. Okay, so I'm simplifying each piece separately, just like I did in that previous problem. So starting with this, I've got c over d. It has the d, but it's missing the c. So I'm going to multiply in a fancy one of c over c. And then minus the next piece, which is the d over c. So here it has the c, but it doesn't have the d. So I'm going to multiply in d over d, just another fancy one. And then in my denominator, I've got d over c again, but for my overall denominator, the LCD is just c. So this actually is the right denominator. And then plus 2. Technically, this is 2 over 1, if that makes you guys feel better about multiplying fractions. And I'm going to multiply this by c over c, because my LCD down here is a c, so I have to multiply that in. Okay, next step, we're going to simplify everything up. So I have c times c, which gives me c squared over d times c. And then minus d squared over, it's either c times d or d times c, it doesn't matter, so you can write it in either order. And then over d over c, which hasn't changed, and then plus 2c over c. Okay, so now again, just like the previous problem, if you look in the numerator, these now both have the same denominator. So I can add, or I guess subtract, the c squared minus d squared over my common denominator of dc, and then divided by d plus 2c over my common denominator of c. All right, so the next thing we're going to do is we're going to write that as division, because technically we're taking this piece right here and dividing it by this piece down here. I'm going to skip a step if it's okay with you guys. So we've got this piece, the overall numerator, and like I said, we're going to be dividing it by this piece, and dividing means multiplying by the reciprocal. Okay, so I was more explicit in writing out each step in the previous problem, but like I said, I think you're okay to skip one of these steps. So if we look for common things we can cancel, this is a d times c, which means each piece is a separate factor. That part gets confusing for people. D times c, each piece is separate, but like a c squared minus d squared, as soon as you get subtraction involved, this piece is one factor. Same thing with the addition. D plus 2c, that thing is one factor. So this one factor of c can cancel with this one factor of c because they're identical, but there is nothing else that you can cancel. Like I've said before, it's very tempting to cancel these d's out, but this d is part of a c squared minus d squared that can't be broken up. So I have c squared minus d squared, which, just so we know, that actually is the difference of squares, but it won't do us any different, or it won't do us any good, I guess, to factor that out because it won't cancel with anything. And then I have d times d plus 2c. So two options. You can do what we did on the front on that previous page, and you can do the distribution, or you can just leave it like this. I don't care either way. The back of the book actually isn't consistent. Sometimes they do one way, sometimes they do the other. So whatever, as long as you cancel the right pieces and it's simplified. So that's the first method, kind of dealing with each thing separately. And then the second method that we're going to work on. And so just so you know, when you're doing complex fractions, you can do whatever method, strikes you as easier or you're more comfortable with or whatever. So this one is you find the LCD of all of the denominators. Okay, so I'll explain what we mean here. So if we look at part A, we've got a denominator of x, a denominator of y, and a denominator of x. Okay, so with all the individual denominators that we have, we're going to find the LCD. So the LCD of x, y, and x. So basically we want to know what are x, y, and x all going to go into, and that would be an xy. Okay, I don't need 2 copies of x, because remember we only need it the greatest number of times it appears. Here it only appears once, here it only appears once, so we only need it once. So what we do with that is we take the entire complex fraction, we multiply the numerator by xy, and we multiply the denominator by xy. So really, it's like we're taking this big fraction and multiplying it by a fancy one. Okay, so that's the first step. We figure out the LCD of all the denominators, and we multiply top and bottom by that LCD. So we've got that part. Next part is that the xy that I have right there is going to get distributed. It's going to get distributed to the 1 and it's going to get distributed to the 2x. Then in the denominator, it's going to get distributed to the 3 over y, and then it's going to get distributed to the 4 over x. Okay, so I will walk you through exactly how that happens. So let's work on each piece. So the 1, that gets multiplied by an xy. Then plus 2 over x, that gets multiplied by an xy. So basically every piece in every spot is going to get multiplied by the LCD. That's how this method works. So then I have, in the denominator, I have a 3 over y right here, and it's going to get multiplied by the xy. And then finally, minus 4 over x, that last piece that I have right here, that gets multiplied by an xy. Okay, so here's where we figure out why exactly we did that. So if we look at all of the denominators, like 1 times xy, that's just going to be xy. But here, when I multiplied 2 over x times xy, this xy is technically multiplying the numerator, so I have an x and an x that can cancel out. And so what I just did is I got rid of my denominator. So I no longer have this weird complex fraction of fractions. Then down here, same thing happens with the y. This y will cancel with this y, 1 copy in the numerator, 1 copy in the denominator. And again, this x will cancel with this x. So the important part, the reason why we did this method at all, is because now all my denominators are gone. So now look what we have. So 1 times xy is just an xy, plus, and then these x's canceled, so I have a 2 times a y, so just a 2y, and then over, down in the denominator, I have a 3 times an x, and then minus, then I have a 4 times a y. Okay, because of the addition and subtraction, this is 1 unit, and this is 1 unit. You cannot cancel 2's or y's or x's or anything. They are a joint pair. You either cancel the whole thing or nothing at all. Okay, last problem. Nice short set of notes for you. We're going to do the same technique down here. So here's one denominator, here's another denominator. Hopefully it's getting pretty easy by now for you guys to figure out what the LCD should be. So just between the b and the a, it's just going to be b times a, or a times b, or whatever you want to say. I always do alphabetical order. Okay, so the LCD is a times b, so just like this one up above, because we're doing the second method this time, we're taking the whole numerator, all the complex fractions there, and multiplying it by an AB, and we're taking the whole denominator and multiplying it by an AB. So really, if you look at the whole overall complex fraction, it's like you're multiplying it by a big fancy 1. So just like the one up above, the AB gets distributed here, and then in the denominator, the AB gets distributed here and here. And we're going to see what happens. So I have a over b. That is going to get multiplied by my LCD of a times b. And then I have plus 1. That is going to get multiplied by ab. And then in the denominator, I start with 1. I'm going to write these both at the same time so I don't switch pens a million times. So I have the 1 minus b over a, and they both get multiplied by an ab. I don't know why I didn't think of this earlier. Okay, so everybody gets an a times b. And when I distribute that a times b, the exact same thing is going to happen as what happened with part a. My denominators are all going to cancel. So here my denominator of b cancels with the b that I multiplied in. No canceling here, but that's okay because I didn't have a denominator anyway. Same thing here. And then my denominator of a cancels with the a I just multiplied in. So now I no longer have a complex fraction. I no longer have a fraction of fractions. I'm just going to have a regular old fraction. So here I have a times a, which is a squared. And then plus 1 times a times b, so that's an ab, over 1 times ab, so that's ab, and then minus b times b. If I had the possibility for anything canceling, I could do a little bit more factoring. Like here in the numerator, I could factor out an a, and here in the denominator, I could factor out a b, but nothing would cancel even if I did do that. And remember, this is a package deal, this is a package deal. You cannot cancel out little bits and pieces. I will say that over and over again until it's drilled into your head. Okay, so nice short notes for you. So we will be working on some complex fraction stuff next time I see you.